Hi. Today we're going to talk a little bit more about some atomic structure and build a closer picture to what we know as the modern atom. But before we get too far into things, I do want to ask a couple questions, give you a chance to review some previous content. So hit the pause button if you want to answer these questions. But otherwise, I'm going to get started. Looking at atomic particles, we know our atomic particle options are protons, neutrons, and electrons. If we're saying one difference between these isotopes of neon, notice that we have the top numbers. We know the bottom numbers to be 10 from our periodic table, link in the top corner. Obviously, they're all number 10, the same number of protons. We're talking about atoms. They're electrically neutral, same number of electrons. So the only reason why we'd see a difference is that there is a different number of neutrons in each of the isotopes. There's 10 in neon 20, 11 in neon 21, and 12 in neon 22. Based on natural abundances, if we're looking at this number of 90.9, obviously much larger than the other two, it's going to affect the atomic mass and draw the average closest to it. So I would expect that the atomic mass for neon would be closest to 20. If you look it up on the periodic table, I believe it's 20.18 or something close to that. So for today, I wanted to show you some fire. What we have here is a setup where methanol is burning. Now, methanol burns with a clear or near clear flame. So all the color that you're seeing is that a compound was added to the methanol and dissolved. So as the methanol is burning, that energy is interacting with the compound shown here. So I think some immediate questions that come to mind for me is, why is this happening? How are we seeing different colors when it's the same methanol that's burning in each case? Obviously, the variable is the compound. So we need to talk about how the energy interacts with these compounds. In terms of energy interacting with compounds, the energy can be given to a compound in any number of forms, like electrical energy, thermal energy, mechanical energy. We have here striking a lighter. You have gas discharge tubes on the top, which are actually not unlike a cathode ray tube, where a high amount of electricity is causing this something to happen. But I want to take a step into that something before we talk about how energy interacts with the atoms. We kind of have to talk about how energy already exists inside an atom. What we see here is a Rutherford atom. And keep in mind that the electrons have a negative charge. The nucleus contains protons with a positive charge. So there is an electrostatic attraction going on between the nucleus containing protons and the electrons outside the nucleus. So in a way, that electrostatic attraction is holding the electrons in the nucleus, but there's also this ability of the electrons to not get pulled into the nucleus. And so in the same way that we talked about electrons having a charge and a mass, there's this third property that electrons also possess that can change, known as energy. And it's just something that's completely different from all the others. You can say an electron has mass, charge, and energy. In relating the energies of the electrons, so as a function of position, that's where we can actually make a distinction as to how that energy that's coming into the atom interacts. The electrons don't fall into the nucleus, as I said, because of that minimum energy that they have. And we're going to call that a ground state. That's where all electrons are at the minimum energy. That said, electrons can absorb energy. Electrons can have differing energies. They can have more than the minimum. And when they do, the electrons that exist up at these higher energies we would call excited. But I do want to relate back this idea of excited states to what that might look like on a structural level. So if I can draw a very poor atom next to this image that I have from the previous slide, we're going to say that's our nucleus, and I need to switch back. We're going to have our electron at some distance here. So here's our nucleus, there's our electron. As the energy comes into the atom, it interacts with the electrons that are outside the nucleus well before the nucleus is ever brought into the equation, in part because the energies, there's a question of compatibility, but also just physical distance. The nucleus is far in the center, the electrons are well outside. But if the electron absorbs energy, and enters what we call one of these excited states, like I said, the energy is one of these intrinsic properties, and it is related to distance. It is fair to say that when an electron is in a low energy state, it gets closer to the nucleus. That minimum energy being the ground state's minimum, right? If electrons have more energy, a way that you can think about that is that that energy manifests in the electron moving farther away from nucleus to some outside location. And it's no longer existing in that close location to the nucleus. So if we're going to relate energy and location, low energy is close to nucleus and high energy is far away. And so you can actually see the electrons move. Well, you don't see the electrons, but electrons will move farther away from the nucleus as energy is added to the atom. This process of exciting the electron creates this excited state. But those electrons, as they are further away from the nucleus, are inherently less stable because energy and stability are opposites. What we have here is an arrangement of stones that I would consider relatively unstable and therefore at a high energy. It took a lot of time and a lot of precise location to make that structure, and if any sort of additional energy interacts with it, it might collapse. If you instead have the bunch of stones in the background that are on the ground, if energy goes by those, well, maybe they might move over a little bit, but they're not going to like topple all over each other and fall. There's no fall to happen. In much the same way, the electrons that are excited are unstable, and after some amount of time, usually a small amount of time, will return back to their ground state location, and therefore their ground state energy. When that happens, regardless of how the energy is added to the atom, the energy is always released in the same way. So this is your high energy electron. This is your lower energy electron. And when you make that transition, you can't go from higher energy to lower energy with no change. Energy came into that electron to get it to the high energy. That has to come back out. When energy is released, it might come in various forms, but the energy is always light. There is some sort of light wave that gets released from the electron as this drop happens. This is what we've observed to happen, and that's where you're getting this process of like glowing tubes and colorful fire. But speaking of color, we should probably put these two thoughts together, because everything I just said is wonderful, but those transitions, like why are we seeing different colors when we're getting different atoms? What is making that difference? As a bit of a refresher, we know that there is this electromagnetic spectrum where on one side you have small wavelength and high energy, and then large wavelength and low energy, and we have all the different kinds of electromagnetic radiation, including visible light. In general, we've got our purple with our high energy, in specific, but relatively high energy, and red light being relatively low energy. So when we look back at our flame and you saw your lithium with the red fire, the light that you're seeing from that is lower in energy than you would see from, say, a potassium fire that's violet, which might make you sit there and try and reason like what's going on. So we can actually stipulate that when an electron makes a certain jump in energy and a different electron makes a different jump in energy, that different light gets released. That would make sense because color is related to energy. Here we have a small energy jump, which would correspond to a low change in energy. So this would probably be some very wide, I'm going to change the color. Some wide red light. And then when you have a larger jump, that's a high energy change, and that would indicate, say, a purple light with a much smaller wavelength is released. So in a way, like that's kind of your explanation for where the colors come from. But why the different size jumps? And I think the biggest explanation for the different size jumps is from the nuclei. Because while all nuclei of a given element have the same number of protons, if this one was, say, lithium and this one was, say, potassium, there's a different number of protons. And so if there's a different number of protons, there's a different level of attraction, a different amount of charge. And so that different charge yields a different attraction, which then impacts the location and the energy of all of your electrons in your atoms. Simple as that. However, that's not really where the interesting thing happens. The interesting part is that if you were to take some of that, those tubes that we saw before, and pass that light through a prism, you would actually see something very interesting. What we have here is our visible spectrum of light, that full rainbow that we're used to seeing. And then what you have here is the light that you get from just hydrogen. That purple light isn't really purple. It's actually made up of several different individual light colors that get separated by a prism. And you know that if you put sunlight through a prism, you get the full spectrum, but we're very much not getting the full spectrum here. In fact, this is called a bright line spectrum because it only shows specific bright lines. This is what the work of the scientists Niels Bohr and Ernest Rutherford, the same Rutherford, they all kind of worked together for about 10 years. This is what their work really found that was interesting. Looking at those specific colors of light, if we relate all of this all the way back to location and electrons, each of these corresponds to a different size jump, with the purpler light being larger and larger jumps, closer to your nucleus. But more importantly, there's no orange line for hydrogen. There are several lines for iron, some oranges, yellows, greens, all that, but there's no orange line. And since there's no orange line here, it's more, this kind of leads to the discussion that certain jumps don't happen. Now, Bohr and Rutherford, when you're talking about science and these particles, you have to work really hard to separate desire and personification. It's not really that certain transitions don't happen. They made the suggestion that certain transitions can't happen. So the Bohr model of the atom builds a model that shows your nucleus existing, sure, but more specifically, once you build your nucleus and put electrons into it, you have to kind of set some rules to say electrons can actually only exist at certain prescribed energy levels, which correspond to certain distances. So when an electron absorbs energy, there might be a certain amount of energy that it can absorb to jump up one energy level or two. And then when it comes back down, you have to remember that the color of light that it releases is a function of the size of the jump. And because the sizes of the jumps are fixed, the colors of the light are also very, very fixed. All those lights mix together, and that's the color that you see when a substance burns or that light goes off. But the whole idea is that the Bohr model and this whole process of putting the light through a prism is illustrating that there's certain gaps in the energy band that are impossible. This is how one fire with different compounds in it can produce different light. The fire is giving out all sorts of energy, but the atoms only interact with certain specific energies themselves. So the whole process of excitation emission has to do with absorbing energy, electrons go up, they fall back down, and release the energy as light. And this process happens continually and constantly. It's been happening this whole video. The color of my shirt you see because light hits it. The compounds get excited and emit a certain color to the camera that picks up and is now playing on your screen. That color is made up of several small bands of light, which correspond to very specific energy jumps, and those are the only allowed energy jumps for that atom in that compound. And that's what causes all the light that you're seeing and all the color you're seeing around you. Thanks for watching.